If I have an equation like the cosecant of x minus the square root of 2 equals 0, then this is an equation involving a single trigonometric function. There's only a cosecant in it. There's no sine, there's no cosine, there's no tangent. So this is what we mean by equations involving a single trigonometric function. Here's another one, the cosecant squared of x minus, 2, I guess, equals 0. Here's another equation involving a single trigonometric function. Now, cosecant is squared here, but there are still no sines or cotangents. Lastly, you might see something like this. Cosecant squared of x plus cosecant of x minus 3 equals 0. There's still only cosecants in this equation. So that's what we mean here. We may have squared, or we may have terms with more than one term with that function in it, but there is only one trigonometric function in each of these. I'm going to start with this first one. In fact, I'm not sure I'll do these other two. They were just examples, but I do want to solve this equation as a way of getting to sort of the heart of what we want to do in this subsection. So as we've talked about in previous videos, the way to solve a trigonometric equation is to isolate the trigonometric function first, and then solve for the function, and then solve for the variable. So I'm going to solve for cosecant first by adding the square root of 2 to both sides. That gives me the cosecant of x equals the square root of 2. Now I could look that up in a table, but it may not always be quite that straightforward, so it's worth taking a deeper look at the analysis here. So let's next recognize the fact that cosecant is 1 over sine. So I can replace cosecant with 1 over sine. So 1 over sine is equal to the square root of 2. Now, I don't want 1 over sine, I want sine. So what I might do next is take the reciprocal of both of these. It's important to note that what I did here was replace cosecant with its equivalent. I have not flipped this over. I have replaced it with its equivalent. Now what I'm going to do is take the reciprocal of both sides, and that gives me the sine of x equals 1 over the square root of 2. I know where the sine is equal to the square root of 1 over the square root of 2. It's at pi over 4. So if I were to draw that angle there, this angle here is pi over 4. I know that the sine of that angle is 1 over the square root of 2. So one of my answers is pi over 4. Plus or minus, actually I don't need the minus, just plus 2 pi k, where k is an integer. This notation, by the way, literally means k is an element of, it's a funny looking E. This symbol means is in the set of, or is an element of the set of the integers. Z stands for all the integers. And remember that integers are positive and negative whole numbers and 0, right? So if k is in the integers, then k can be 0, k can be a positive whole number, or k can be a negative whole number. When k is 0, we get pi over 4 plus 0, which is pi over 4. That's our primary solution, okay? So that's one answer, but where else is the sine equal to 1 over the square root of 2? The other candidates are the reference angles of pi over 4 in the other 3 quadrants. In this case, notice that our sine is positive, so that means it cannot be in quadrants 3 or 4. It can only be in quadrant 1. So now if I eliminate the possibility that it's in quadrants 3 or 4, that there's a solution in quadrant 3 or 4, what's left is the angle with reference angle, call that t prime, pi over 4. What is that angle? It's the angle that starts here and goes around to there. So it's all the way to pi, which would be 4 pi over 4 minus 1 pi over 4. So this angle is 3 pi over 4. That gives us another solution. X equals 3 pi over 4 plus 2 pi k, because I can go to this angle and get a solution, or I can go to this angle, which is 3 pi over 4 plus 2 pi, and get a solution, or plus 2 pi times 2, or plus 2 pi times 3, and so on. Now, this time I can't combine my answers because I don't have if I go to my first solution and then I add pi to that, I end up in quadrant 3. So in this case, that's not going to work. There are cases where it will, and we'll talk about that in just a minute. But one of the things that you can, one of the ways that you can tell that this solution, x equals pi over 4, is not going to have a matching solution in quadrant 3, is that to get to the next solution of the next solution of this equation that's related to pi over 4, you have to go 2 pi, and that's because sine, and therefore cosecant, they have periods of 2 pi. So to get to the next solution related to this solution, you have to go around 2 pi. To get to the next solution related to this solution, if you just went pi, you'd end up in quadrant 4. There's no solution there. We determined that earlier. Sine is not positive in quadrant 4. So to get to the next solution related to 3 pi over 4, you're going to have to go all the way around 2 pi. So in this case, you need both of these solutions plus 2 pi k, and then don't forget to mention at least once that k is an integer. K is an element of integers. Now, sometimes you're asked for all solutions, and that's what we've been doing so far. The instructions here might say something like, find all solutions of the equation cosecant x minus the square root of 2 equals 0. But equally, it might say, find all solutions in 0 is less than or equal to x is less than or equal to 2 pi, or in the interval 0 to 2 pi. Those two things mean the same thing. These two notations mean the same thing. The first one's in inequality notation, the second's in interval notation. Sometimes you'll be asked to find solutions only within a certain stretch of values. I hesitate to use the word range of values there because that's actually restricting the domain, not the range, but this stretch of values. So when that happens, we now know how to find all solutions, right? We just add plus 2 pi k. When I'm asked to find the solutions within an interval, it's usually going to be within the interval 0 to 2 pi, and that just means once around the circle, right? So I found the first one at pi over 4, the second one at 3 pi over 4. There aren't any others in the first circuit, the first go around. That means I'm done. So if I'm given this restriction on the domain, I actually just need to leave off this part of the solution. It's important to know when you're being asked for all solutions to include this information, and when you're asked for the solutions within a particular domain, specifically 0 to 2 pi, that you leave those off. Right? I have found the only two solutions in that range of values, 0 to 2 pi, that satisfy this equation. So the context matters, the instructions matter. Pay close attention to whether you're being asked for all solutions or solutions within a restricted domain. All right, let's take a look at another example. The instructions here say to find all solutions of the equation, and that's all solutions. There's no domain restriction given anywhere. Find all solutions of the equation 2 times the tangent squared of theta minus 6 equals 0. Once again, I'm going to try to isolate this. I'm going to try to get it down to tangent squared. First of all, so I'm going to add 6 to both sides, which gives me 2 tangent squared of theta equals 6. Then I'm going to divide both sides by 2, which gives me tangent squared of theta equals 3. Now, I don't know where the tangent squared is 3, but I might be able to figure out where the tangent of that of the angle is, whatever the value is I get when I take the square root. So let's take the square root of both sides. The tangent of theta equals the square root of 3. Now, I could look that up in a table, or I can just remember that, let's see, I have sine of theta, cosine of theta. When I'm doing this for myself, I often just say sine and cosine, and then 0, pi over 6, pi over 4, pi over 3, pi over 2. And then to fill this out, I have the square root of 0 over 2, the square root of 1 over 2, the square root of 2 over 2, the square root of 3 over 2, and the square root of 4, which is 2 over 2. And then I go backwards. Square root of 2 over 2, square root of 3 over 2, square root of 2 over 2, square root of 4 over 2. And then what I'm looking for is a tangent, so I need to know what the sine over the cosine is. The sine over the cosine, the sine over the cosine. So I have a tangent row as well. And here, sine over cosine is 0. Here, sine over cosine, the denominators will cancel, so I have 1 over the square root of 3. Square root of 2 over the square root of 2, or even the square root of 2 over 2 over the square root of 2 over 2. Any number divided by itself. Square root of 3 over 1 is the square root of 3. And there's my answer. If I had found it back here, I could have stopped, right? This is the value I'm looking for. That's what I have here. So the tangent of this angle is the square root of 3. And this angle is pi over 3. So my solution here is theta equals pi over 3. Now that's not my solution, but it's the sort of primary solution. It's the first solution that I can come up with. Now that I've done that, let me erase the table here, give myself some more room. And I'll give myself a unit circle and some axes. Pi over 3 is this angle right here. All right, so there's my reference angle, pi over 3. And I want to look at the tangent is positive. There's no sign in there. So the tangent is positive. So where's the tangent positive? Well, it's positive here and here. So I'm going to be working in quadrant 1 and quadrant 3. So I want reference angles of pi over 3 in quadrant 1 and in quadrant 3. So there's my second angle, my second reference angle. This actual angle is 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. So the other answer here is 4 pi over 3. Now I've been asked for all solutions. No domain restriction has been listed, so I'm going to say plus 2 pi k, where k is as an integer, and here plus 2 pi k. I'm also, however, going to make the observation that these angles, that's not a very bright color, let's try pink, these angles line up, they create a straight line. So that means to get from one to the next, I only have to add pi. And that means that another way to write this solution is theta equals pi over 3 plus 1 pi k, or just plus pi k. I do still need to include k is an integer. So I can either write both of these two lines, or I can write it as a single line. But you need to make sure you change the plus 2 pi k's to plus pi k when you do that. Now I hope it's obvious to you that this would happen here, because the period of tangent is only pi, not 2 pi. So it seems sort of natural that if you're working with a tangent function, that you should be able to do this as a single solution, a single line, rather than having two separate lines here. This is equally correct, but this is a lot more compact, and I don't know, I kind of like it better. If you'd been working on an equation, and it wouldn't work here because we'd have a plus 6 and then a minus 6 and then a minus 3, and then you'd be taking the square root of a negative number. So you wouldn't have, you wouldn't reach this, you wouldn't come into this situation from this exact problem. But say you'd been given this problem, but where the right-hand side was negative. Well, in that case, my tangent would be negative, and so I need to be looking at the reference angle pi over 3 in these two quadrants. So my answer would be not 1 pi over 3, but 2 pi over 3. Here, let me put those in. I'll do them in green. So everything that's related to the second version of this question, this one here, is going to be in green. So my first reference angle is there. My second one is there. And again, these line up, right? They fall into a straight line. Again, that makes sense, because even though I'm dealing now with a negative solution to the equation tangent of theta equals a number, tangent still has a period of pi. So once I go around once I find a first solution, I'm only ever going to have to go around half the circle to find a second solution. The answer here would be 2 pi over 3 plus 2 pi k, and let's see, 6 pi over 3, so 5 pi over 3 plus 2 pi k, or just 2 pi over 3 plus pi k. So I've effectively ended up doing try it number 2 for you in this video. That's not what I set out to do, but that's what ended up happening, so that's okay. Every once in a while that might happen. that's all I'm going to do for this video. The next one is the first time in which we'll look at solving trigonometric equations using a calculator, or really doing anything using a calculator. So that's our next video.